And I would probably say this is the technique that requires the most creativity and perseverance. Which, yeah, that's sort of like, oh, that doesn't sound like something I want to really endeavor on. Why? Well, you have a lot of different identities. And some of them will work, and some of them will not work. And then they have to also be coupled with other advanced techniques. So, for example, here we have the integral of tan x. And sometimes what you do in these questions is you say, have I ever done a derivative where I just got tan x as the answer? And the answer to that is probably no. You probably haven't done a derivative where you got an answer of tan x, unless, have you done the derivative of the natural log of secant before? Did that come up in any homework in the past? Maybe not, right? The derivatives of the natural log of secant would not be hard to do, right? It's a simple chain rule. You'd have 1 over secant, and then you'd multiply by the derivative of secant, which is secant x tan x, and secants would cancel out, and you get tan x. Oh, that's nice. But how do we work backwards from this? Well, one of the things you could do is if you're stuck and you're like, yeah, tan x isn't one of my derivatives, so I need to change it to something. And if I change it to sine x over cos x, since the derivative of sine is cos and the derivative of cos is negative sine, you might say to yourself, maybe this is one I can use substitution with the chain rule. So what should I choose as my inside function? I should choose the bottom. We'll let u equal cos x, and the derivative is negative sine x, so sine x dx would equal negative du, and we can use substitution here, which comes up as the natural log. Technically, add absolute values there. Maybe they show up. Yes, they do. And then I get negative natural log of cosecant x plus c. And that negative out in front, you can use your log laws to put it as an exponent of -1. So we also have to really remember all of our log laws in this situation. And we get natural log of secant x plus c. And I would say this is one of the easier ones. So, if you get a trig function, you have to do the integral of. And it's not something you can do directly, although you will try first all of your direct strategies. Then choose an identity. Now, do you see that you could change tan to sine over cos? You could also change tan to 1 over cotangent. So this is where the perseverance comes in. If you choose an identity that doesn't work, right, it may mean you need to choose another identity. And then if you choose another identity that doesn't work, you might have second thoughts and say, well, maybe the identity I chose the first time would have worked, but I made a mistake. Like, these are all possibilities, which can get frustrating, because sometimes you will choose the right identity first, but then make a mistake that makes it not work, and then have to try something else, and eventually you have to go back to the identity you tried the first time and do it again slower. And sometimes you do it again slower and find out, no, it really didn't work, and I needed to choose something else. Show that the integral of 1 over secant x equals the natural log of secant x plus tan x plus c. Okay, now on these ones, if they give you the answer, one of the things that can be a strategy for helping you is start with the answer, do the derivative, and see what happens when you do the derivative. And that might give you ideas or patterns to be able to work backwards. So sometimes at the beginning of these ones, it is not wrong to cheat and look at the answer and use the answer to work backwards, because sometimes our brains don't think of the right strategy right away, especially if they're creative strategies. Sometimes we have to experience seeing the right strategy or the creative strategy a bunch of times before our brain is able to think creatively that way. Does that make sense? So, what can I do with secant? Well, I could decide to multiply secant by secant x plus tan x over secant x plus tan x. Here I'm definitely cheating by using what's in the answer. Do you see that if you had natural log of secant x plus tan x, and you did the derivative, you would get a 1 over secant x plus tan x, and then have to multiply by its derivative afterwards. So by cheating and looking a little bit at what the answer was, I wanted to have that on the bottom. So I just put it on the bottom, but you can't just put something on the bottom unless you compensate by also putting it on the top. Okay? So that's the first step. I got it on the bottom now. If I have that on the bottom, that seems to be what I would like to make my substitution. And if I let u equal secant x plus tan x, then the derivative of secant is secant x tan x. And the derivative of tan x is secant squared x, which, if I wanted to, I could factor out the common factor of secant x. Oh my goodness, look how nice this works. That's like exactly what I have on the top. Or I could have just multiplied out the top. And notice that's exactly what I have. So now when I do my substitutions, this is beautiful. Then we get our answer. Now on this one, if you hadn't been given that answer, that would take a very long time to think of this as a strategy. It would be very, like, this would be a try over the next couple of days or weeks. Spend a couple hours on it every day kind of question and see what comes up. So this one, it's sort of like the answer showed us a hint for doing it. Next one, we have a cos squared. And when you have a cos squared, you can always think of sine squared plus cos squared equals 1. We also have a cos 2x. And the cos 2x, you have 3 formulas for cos 2x. Okay? This is a great example of perseverance. You have 4 different things you could try as your first step. And you could try one and see if it worked, and it may or may not work. So with that in mind, the first thing I need you to feel is not bad when you spend 10 to 15 minutes and feel like you don't get anywhere. You should feel normal. I know you don't like to hear that. Because what do we like? We like it if there are steps that we can follow, which make these really easy every time we do them. Okay, that's, as students, that's what we like. I know that. Okay, I can tell you that if you do a lot of these, you will get good at them and be like, oh, I recognize which steps I should use. But that only comes after you've done a lot of them. So it's not like there's an easy fix either way. Okay. There's one of my cos 2x formulas. So instead of taking you down and showing you a bunch of methods that don't work to begin with, let's say we chose that one. And in this case, inside we have a 2x, so it's like my alpha is 2x. And in that formula with squared, if I have a 2x there, then I would have cos 4x over there. Because it's cos 2 alpha if my alpha is 2x. And here too, what makes this interesting is we're not thinking about using the cos 2x on the left side of the formula. We're thinking about having our cos 2x with the squared inside the formula. Then if I rearrange this cos squared 2x to get it by itself, this becomes cos 4x plus 1 over 2. What am I trying to do here? Initially, my integral has a squared with a cos inside of that with a 2x inside of that. That's a triple chain rule if you did the derivative, right? Triple chain rules for integrals are not nice things to deal with. Okay? By changing it to the cos 4x, do you see that cos 4x just has a chain rule, and the chain rule is just the 4, which we definitely can deal with an integral by dividing. So that seems nice. And I'm going to unadd those fractions, so I can write cos 4x plus 1 all over 2 as cos 4x over 2 plus 1 half, because then I can integrate them separately. And in fact, at this point, these are relatively easy integrals. I don't need any substitution, because what's the integral of cos? Sine. So I should have sine 4x over 2. But it would have a normal chain rule of multiplying by 4 if I did the derivative. So I have to divide by 4 with the integral. And how easy is it to do the integral of a half? Super easy. That'll be 1/2 x. So once I came up with this in the green box, life was easy. But coming up with that idea from the green box, especially because you don't have a formula sheet, so you have to know all of your double angle formulas really well. Of all the formulas up here from previous years, in the AP we don't use the alpha plus beta ones very often. But the double angles come up a lot. So if you're like, which one should I really know? Know your double angle formulas. And do you know how to find all 3 cos double angle formulas if you know one of them? Like most people, I don't know, I find that most people have this one as their main cos double angle. And then because sine squared plus cos squared equals 1, if you want to write the other ones, right? If, like in this case, I only had cos squared. So if I want only cos squared, well, sine squared is 1 minus cos squared. And if you do that simple substitution, you're going to get 2 cos squared alpha minus 1. I mean, you can memorize all three if you want, but if you have one memorized, you can always do a simple substitution to find the other two. That's how my brain works. My brain says, what is the minimum amount of memorization you need to do? And then figure out from there. And then, if it happens too often that you're having to figure things out, then your brain just says, well, just remember this other one as well, because you're using it often enough. Okay. I have a sine 2x and a 1 plus cos squared x inside of a square root. Now, I'll logically go through what our brains should see in this question and go through. Always try your simple methods first. So I would probably start with thinking, maybe this is substitution. I see a 1 plus cos squared x inside of a square root. I would like to make that my u and see what happens. That's probably how I would start. And then what's the derivative when I make that my u, right? That's how I think I'd start. My derivative would be 2 cos x and negative sine x. Does that match with what I have on the top? Not directly, but do you see the identity? Okay. And so sometimes what I would do in a question like this as well is, like, this one I would start with this, and if I got stuck here, which I hope you wouldn't, because I hope you see it, but if I did get stuck there, I might also go, okay, this is a trig one. I have a sine 2x. What's my double angle formula for sine 2x? It's 2 sine x cos x. I have a cos squared. I just start writing out identities that may help me. The second one doesn't help me in this question, but the first one does. Like, hey, I have a 2 sine x cos x with a negative. That means negative du would be sine 2x dx. And with that substitution, my integral becomes easier. Right? This is u to the negative a half. How do we do powers? Add 1 to the exponent and divide by the exponent. So if I add 1 to negative 1/2, I'm going to get positive 1/2. Divide by a half, which is the same as multiplying by 2. I mean, if I were you, I would have probably written it like this. Right, because we get into that methodology of add 1 to the exponent, divide by the exponent as our typical power rule integration technique. Secant to the 3/2, like, you're like, we see that and you're like, really? To the 3/2? Okay. 10x. So another strategy that I start to do with these is first of all, I think, do I have any identities? And the answer with just a 10, no. Just a secant to the 3 halves, obviously no. But I start writing down things that I know. So what do I know? I know that, so identity-wise, I've got tan squared theta plus 1 equals secant squared theta. Okay? Derivative-wise, the derivative of tangent is secant squared. The derivative of secant is okay. So I put things down that I see in the question. Why are these derivatives important? Well, if I do a substitution, I need to do the derivative. Okay? So what could happen in a question like this? I wrote down the tan squared theta plus 1 equals secant squared, but I don't have anything squared. So right now I'm going to leave that. I might come back to that because could I make secant squared? Yes, if I also divided by secant to something, I could play with my exponent laws to make it work. That may be something I should do. But that seems messy as the first thing, so I go like, oh, maybe I'll wait. Because there are messy techniques that might be the right technique, but usually we like to leave the messiest techniques for the last thing we want to try. We want to try easier things first, and hopefully one of them works. Next, I could decide maybe I want to make my u tan x. Does that help me get rid of everything else? Well, if I made my u tan x, my derivative of secant squared, does that get rid of this completely? It doesn't match up perfectly. So then I say, well, if I make my u secant, then my derivative is secant tangent. Does that maybe work? And the answer to that one will be yes. If we make our u equal to secant, our derivative is secant x tan x. Okay. How could I rewrite this? Instead of have secant to the 3 halves x, how could I rewrite this to have a secant x tan x? And your exponent laws, secant to the x to the 1/2 times secant x to the 1, right, would be secant x to the 3 halves. Because your exponent laws, same basis, add the exponents, 1/2 plus 1 is 3 halves. And then when I do my u substitution, I just get u to the half du. And now everything is easy. Add 1 to the exponent and divide by 3 halves. Substitute back. So some things that we see, right? We had different options for playing around. Choose an option, see how far you go with it. Okay? Had you chosen the tan option, I'm going to just show you what it would look like to choose a wrong option. Okay? Had I chosen this as my u, right? If u equal tan x, then du would equal secant squared dx. And my original function okay, I would need to get a secant squared in here. So if I have a secant squared, I would have to divide to get that secant squared, I'd have to divide by a secant to the half, right? So that I subtract my exponents, and 2 minus a half gives me 3 halves. So I'm using my exponent rules. And my substitution right now would get rid of all of this, but still have this left. And if something's left and it's not clean, like we need our substitution to be clean and have everything go away for us to continue. But in this section, my secant to the half doesn't go away. So I have a problem. Is there any way I can manipulate things to make it go away? I don't see any way that I can manipulate it to go away. Becomes a problem. Okay? By making the u secant x, my derivative gets rid of tan x and part of the secant x's, which allows us to get rid of everything and makes that the better option. Okay? Will you choose the best option the first time, every time? Absolutely not. Right? Sometimes you'll choose an option and you'll get to this point and be like, okay, I could get rid of these things, but I still have a problem with this. Can I think of a way with what I'm in to also get rid of that? If the answer is no, back to the drawing board, try something else. Right? Cos to the 5x. And if you like, you can look on YouTube. There's people that have, like, if it's an odd power, you should do this strategy. If it's an even power, you should do this strategy. But right now, we're just going to use the idea of, okay, what strategies do I know? What identities do I know? So for cos, I know that, so off to the side, this is what d dx of cos is negative sine. I know that cos squared x is 1 minus sine squared x. I know that two cos squared x minus 1. Okay? Some things that I don't like. I don't like that when I do the derivative of cos I get sine, and I don't have sine in my equation. That kind of bothers me a little bit. Okay? I could get a sine in my equation if I break this up, right? I could write cos to the 5x as cos cubed x with a cos squared x, which would give me a sine squared x, but not just a sine. And I have my double angle identity. This is kind of nice because it would slowly get rid of squareds and replace them with 2x's. So what are we going to do? We got to choose one of those. If I break this up to cos to the 4x and cos x, and I do change this to 1 minus sine squared twice, well, then I should also add to my options that the derivative of sine x is cos x. So at this stage here, I'm kind of like seeing, I see this part as this part. Maybe I can do something with this. So let my u equal sine x, because I've got that cos x dx. What happens as a result? Well, I could either write this as 1 minus u squared squared, but that wouldn't substitute everything. If I actually multiply this out, FOIL it out, I'll get 1 minus 2 sine squared x plus sine to the 4x. And if I substitute my u in there, I get 1 minus 2u squared plus u to the 4. Okay, I don't think it would be bad if you had done the substitution before you multiplied it up. And if you did the substitution before you multiplied it out and then squared it, you would get the same thing. So now we just add 1 to the exponents and divide, substitute back in. And this is what makes integrals so hard, is because in order to do a derivative that simplifies to cos to the 5x, that's all the stuff you need first, and then you'd have to do the derivative and simplify it to find out that that works out. Just kind of crazy. So then if you watch on YouTube, they'll say, if you have an odd power of cos, always do this strategy. Because if it was to the power 7, you see you have cos 4x. And you could use this strategy over and over and over again. What we're trying to develop is a method of seeing possible strategies moving forward. So you don't have to memorize this strategy for this one, this strategy for this one. But seeing lots of strategies opens up your idea for what you could do. So here, you have a cos to the 5x, right? I know that I could get a cos x by itself with the derivative of sine x. I have my identities, so maybe I work with those kind of things and do some substitution. All right, you want them to get harder? No. I'm going to say they don't really get harder. They just stay at this same difficulty with different strategies. So, sine to the 5x, and then I have a square root of cos x. So I could write out all the things, right? Here are all the things I know. I know d dx of cos x is negative sine x. I know d dx of sine x is cos x. I know that sine squared x is 1 minus cos squared x. I know that cos 2x is 1 minus 2 sine squared x. So I'm looking for, when I write out my formulas, Since I had powers of sine, that's why I wrote the minus 2 sine squared x1. Right? I also know that sine 2x is 2 sine x cos x. And after writing everything that I know out, it's still not necessarily obvious which one I should use. So don't feel bad about that. Okay? You actually, from a math learning perspective, I actually appreciate more you trying stuff and having it not like, it doesn't necessarily have to work. The process of just attempting something and seeing where you go with it, and then attempting something else and seeing where that goes, that is the best mathematical thing that you'll get out of this. Just seeing the right answer and expecting yourself to come up with that method right away isn't very helpful. So this is really a lot of problem solving here. So what do I see here? Well, if I break up my sine to the 5 to sine to the 4 and sine, and we'll start seeing this as a strategy of getting an even power for sine and cos rather than an odd power. So we saw that in the last question. I had cos to the 5x. I broke it up to cos to the 4x and cos to the x. Because having an even power allows us to use this. Because if I have an even power, I can now write sine squared x squared. Which I could change to 1 minus cos squared x. Having the odd power and breaking it up will also always get us a single thing with your dx. And if my single thing with the dx is sine x, it's kind of giving me the hint that I should make my u cos x. So this is an observation that we've made by doing 2 questions. I mean, I'm making that observation quickly. Probably in a real mathematical learning environment, I would get you to do 12 of these on your own and struggle until someone in your group would go, hey, do you notice this pattern? Do you notice that when we have an odd one, if we make it even and pull that out, usually that's what is going to happen with our u and our du? So I want you to know is that if I had that amount of time and you also didn't mind being punished by me for making you do hard stuff a lot of times in a row, you definitely would come up with this. Right? So know that you would have that capability. Yes, definitely. You would definitely come up with this. And when you came up with it, like, I feel bad because, trust me, Teddy, you would come up with this. And when you would come up with this, you would feel so much amazingness. You'd be like, oh, I'm amazing. Look what I saw. You have that capability in you. But unfortunately, you also have a test on Monday, and I want to give you time, right, to study more for integration. We're going to do a vertical surfaces activity again tomorrow. So I make my u equal to the cos, which gives me this part. And anytime you have things with powers, it gets this. But you can multiply that all out. Right, we already did 1 minus u squared before. It's 1 minus 2u squared plus u4. Now I can distribute that u to the half It's, right? I'm going to say it's simple exponent rules and expansion stuff. My grade 9s would argue otherwise because they're doing that, but they would not like this part of it. But it's basically a grade 9. This expanding this squared and multiplying your u to the half is grade 9 exponent laws and distribution. Our job though is we wanted to get it into a form where we knew we could integrate, and now they're all powers, so you can just add 1 to the exponent and divide, add 1 to the exponent and divide, add 1 to the exponent and divide to all 3 of them. And I multiply by the, you see I multiply by the reciprocal right away, because you would have 7 over 2 divided by 7 over 2, which would be multiplied by 2 sevenths, you get 4 sevenths. Plug your cos back in. And if you really want to know if you're right, you can take the derivative of this and simplify with identities. You know how not nice of a derivative that would be? Has a bunch of chain rules, right? But you could simplify it. It'll eventually become sine of 5x times the square root of x. So with sine and cos, if you see an odd power, we're starting to notice, make it an even power that gets just a sine x dx or a cos x dx by itself, kind of gives you a hint of what your substitution's going to be. And the last two deal with tan and secant. And tan and secant, you're either going to make your u secant or your u tangent. One's going to work and one's not going to work. So how to determine which one to do? Let me know when you're good, Sean. You're good? Okay. So in purple, in my head here, there's one of my formulas I have it written at the top. I also know that d dx of tan is secant squared. So what I'd like to do before I show you is I want you to brainstorm. I want you to brainstorm and say, would I like to make my u tan x, knowing that's the derivative is secant squared, and knowing that tan squared x plus 1 equals secant squared x? Or would I like to make my u secant x, knowing that my derivative is secant x tan x, and tan squared 1x plus 1 equals secant squared x? Which one of those gets rid of everything? One of them will get rid of everything. One of them will leave either a secant x or tan x left over, which causes a problem. And if you're stuck thinking about it right now, my next thing I would get you to think about is use the derivatives here. Think if you replace the dx with a secant squared dx, what's left? If you replaced the dx with a secant x tan x there, what would be left? And I'll show you what I mean by that before. So if I wanted the secant squared dx, or if I wanted right, those are my two options for my dx's. Either having the secant x tan x with my dx, or my secant squared with my dx. If I have the secant squared with my dx, what would be left after I took that out? I'd still have a tan cubed x, right? And I'd have a secant squared x. If I took the secant x tan x out, I would have a tan squared x, and I would have a secant cubed x. Correct? This one, you would make your u tan x, right? Because that's my secant squared dx. This one, I would make my u secant x. So the question becomes, if I'm making my u tan x, I need to make all of this in the green with tan. Is that possible to change the secant squared to just be tan? Yes. I could do tan squared x plus 1. This makes me happy. This one's going to work. If I look at this one, if I make my u secant x, I'd have to change everything here to secant squared. Could I do that? Yes. I could change my tan squared to secant squared x minus 1. This one would, they both actually work. All of that thinking, if you just would have randomly chosen one and went with it, they both work. But we need to be able to, once you take out that derivative part, the rest of it has to do with the substitution and have it all go away just to be used. So it doesn't matter which one I chose. Here, I let u equal the secant x tan x. Funny, because if I would have went with my gut of what I wanted to do right now, I would have made my u tan x. They both are going to work. If I make my u secant x tan x, I need to rewrite this like I did here with the purple and the green. I just broke it up a little bit slower here. But my tan squared x, I could change to secant squared x minus 1. I still have the secant cubed x, and then I'll put this in purple brackets. No, those are green brackets. I really try to make them purple. There. And now when we do our substitution, it's u squared minus 1 times u cubed du. You could distribute that. You get u to the 5 minus u cubed du. That's easy. if you did your substitution the other way, your final answer would have been tan to the 6x over 6 plus tan to the 4x over 4. Is that right? And it looks totally different, but it is also the correct answer. Isn't that weird? That should bother you just a little bit. That's okay. It's because the answers look totally different. And that would be totally frustrating if you did the right technique and you got an answer, and in the textbook at the back they had this answer, and you're like, my answer was with tan. It's also completely right. Right? So from now on, whatever work you do, you just like, oh, well, I did it right. I just did it differently. And but still completely right. Just take that confidence for the rest of your life, and you'll be delusional, but you'll be very confident.
Is there a scenario where this would be like a multiple choice question and only one of the answers is there?
I don't think they would do that because I think, well, I can't say for sure, but I assume that the people making the exam are very smart mathematicians. And being very smart mathematicians, they would have many times seen this scenario. They wouldn't be like, oh, I never knew there could be two different solutions. They're going to be people that be like, yes, I know that there's more than one solution. And if the one solution is not easy to get, like, had you chosen this method, technically we could change each of these secant squareds, tan squared plus 1, distribute them all, multiply them all, combine like terms, and maybe get the same answer. But that's a lot of algebra work for a multiple choice question. They would realize that and say, this therefore isn't a good multiple choice question. This is better as a long answer question. And as a result, I would go, I don't think they'll ask this, just because of the problematic stuff. But it's one of those things that they won't ask on an exam, but for the next level of calculus, well, you better know how, right? So it's still worthwhile knowing how to do these things and seeing this. So here's our last one. Okay, again, I'm going to do that strategy. I'm going to say I know my ddx of tan x is secant squared x. I know my ddx of secant x is secant x tan x. So I'm going to take my original one and do some substitutions. I'm going to do one integral where I have that separated out. I'm going to do another integral where I have that separated out. Okay. If I took the secant squared out, I'd have tan squared x secant to the 4x. I guess in purple, I'm also going to write out that tan squared theta plus 1 equals secant squared theta. And in the other one, if I took a secant and a tan x out, I'd be left with a tan x and a secant to the 5x. This one is where I would make my u tan. This is the one where I would make my u secant. So I'm going to ask myself, in the green part of this equation, could I change this to only be tangents? Yes. Smiley face. In this one, if I make my u secant, could I change everything to be secant? No, because this tan x is just a tan x. It's not squared. Oh, sad face. This one both won't, that one won't work. So I'm going to let my u equal the tan x. So now I'm going, like, it's not just You could just pick one and try it. That's not a bad strategy. Pick something, try it, doesn't work. Pick something else, try it, doesn't work. But do you see this method that we did here at the bottom kind of leads us to see which one's going to work? Because now I write it like this, and I know that secant squared is tan squared x plus 1. So secant to the 4 is secant squared squared. So tan squared x plus 1 all squared. I substitute for my u's. I have to do some algebra. Can you imagine if this was like a 25 or something as an exponent? Then you'd have to use Pascal's triangle or the binomial theorem. I just added a level of hate to this question. Multiply it out. One of the things you should know if you haven't realized it for yourself yet is you have great algebra skills. All of you. Sometimes you probably don't feel that, but you do. You have great algebra skills. And something like squaring the u squared plus 1 all squared now, it might be time consuming and a little bit annoying, but it's not hard anymore. So a lot of these things, even when I say having to use the binomial theorem, that would be annoying. You'd probably have to look it up a little bit. But the algebra part of it is not hard. You are good at that. Some of these take a long time. The algebra is just tedious, but not hard.